Yeah, hello again. So, we were talking about this sufficient conditions for constrained minima, and after a long derivation we arrived at this condition, that is we would like to have Hessian of the Lagrangian. Note that H here is not the Hessian of the objective function, is the Hessian of the Lagrangian, that should be greater than 0, meaning that the perturbations that you have, that is delta x star here, it should be greater than 0. What kind of delta x star? Delta x star that satisfy this relationship. Okay. For such a delta x star if it is greater than 0, we say that is the condition. But sometimes some books, to make it probably simpler for beginners, will say that Hessian of the Lagrangian, if it is partially definite, they say that is sufficiency condition, but that is actually asking for more. So, what we have written here is less stringent requirement, but then how do you verify it? That is a question. Okay. If you do this partially definite, no problem, but why check more than what is required? Okay. So, in order to check this in the constraint where this is only those perturbations which are feasible, right, that is what we said, we have to consider the feasible perturbations. For those feasible perturbations, how do you verify this? You cannot be checking all feasible perturbations, right. If you have a point here in the vicinity, let us say this part is the feasible perturbations, right, you cannot be checking everywhere, that is endless. No, how much ever you check, somebody may say, oh, you not checked here. If you check here, 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 they will take a microscope and say you not checked here and so forth, right. Then we cannot be doing that, we have to have a condition where we can easily verify this, right. So, this overkill of the requiring the Hessian of the Lagrangian being partially definite, we solve that with this less stringent requirement in a way that is numerically easy. Okay. So, checking this easily brings us to the concept of what is called bordered Hessian. It is Hessian, but it is going to satisfy this perturbation restriction, okay, that is equality constraints and active inequalities first order term should be equal to 0 when you perturb. Okay. This bordered Hessian, which is shown here, okay, the B subscript there denotes it is the bordered Hessian as if it is a boundary. I do not, Hessian is after a person Hess, but bordered is not after a border person, it is just that it is on the boundary, okay, that is what it means. That is shown here. How do you construct the bordered Hessian? What is the size of it? If you see this matrix, we have m columns here, n columns here, we have m rows in the first one, n rows. So, we have m plus n by m plus n, okay, because the first part of it here you see there are m rows and m plus n columns, the second part of it has n rows and m plus n columns. So, total m plus n by m plus n, right. This is a bigger matrix. See, earlier checking this we said no, exhaustively does not make sense, we need a simple condition. The condition is going to head the bordered Hessian. Unfortunately, it is a much bigger matrix than Hessian of the Lagrangian, which is over here, which was only n by n, but now we have to deal with m plus n by m plus n. And what do we check? We check that the last n minus m principal minus of the bordered Hessian should have a sign which is minus 1 raised to m, that is what you are saying. So, first understand how bordered Hessian is written, we are not going to go into the derivation of it. Those of you who are interested in knowing more about where it comes from, you can look at a book by Leuenberger, which is one of the best optimization book for this constraint minimization or unconstrained minimization theory, a book by Leuenberger. You can look at that. I think the title of this is, I think there is one book called Vector Space Methods, another book called Nonlinear Programming. You can refer to Vector Space Methods book where there are some hints given about why this bordered Hessian concept works to verify this condition, okay, this condition which is like an if statement, and we have to get the perturbations which are feasible and check there, So, this is a simple check. The check is, if you construct the bordered Hessian, the last n minus m principal minors should have a sign minus 1 raised to m, where m is the number of equalities plus the number of active inequalities. Again, we emphasize that active inequalities are same as equalities. Okay. So, what are the principal minors? N minus m, last n minus m principal minors. So, the last one is the determinant itself, right. The last principal minor is determinant of the entire matrix. Last but one principal minor where you leave out. I think last time I said other way around, it is not the first principal minor, second principal minor, you have to leave out the last row and last column and take the rest, and then you leave out last 2 rows and last 2 columns and take that. Okay. So, this is the last principal minor, this is last but 1, this is last but 2 and so forth. You have to keep on going up to n minus m principal minors. These principal minors should have the sign minus 1 raised to m, where m is the number of equalities and active inequalities. Okay. That is how we check, very simple check. You have to, if you have let us say 10 variables and 6 constraints. So, n equal to 10, m equal to 6, you have 4, the 4 determinants you have to evaluate of the bordered Hessian, which is constructed in this manner with zeros here and the gradient of the equalities and active inequalities and the transpose of that Hessian of the Lagrangian. All this put together in this form to be m plus n by m plus n matrix. If you have 10 for n, 6 for m, you will have 16 by 16 matrix, and that matrix you have to take this principal minus last n minus m, last 4, and then say that they all have sign minus 1 raised to m. Okay. Let us see this with an example, so that you understand how this works. So, here we have taken a 3 variable problem. Our f is a function of x1, x2 and x3. In particular, we have x1 plus x2 square plus x2 x3 plus 2 x3 square subject to one constraint. So, here in this problem n is equal to 3 and then m is equal to 2, sorry, m is equal to 1. So, let me get the erasure. Yeah. M equal to 1 equality. So, n minus m is equal to 3 minus 1 equal to 2. So, we have to check 2 principal minors of the bordered Hessian. Okay. So, first when you have f, we can compute the gradient. Okay. So, gradient, because first we have to write the Hessian of the Lagrangian, right. So, we have to write L equal to f plus lambda into h. We have only one constraint here. So, if I just do that, gradient of f here is, we have take derivative of f with respect to x1, that will give us 1, that is it, x1 is only in the first term over here. With respect to x2, second term will give us x2 and then third term will give us x3, and then with respect to x3 we have third term will give us x2 and fourth term in the objective function f will give us 4 x3. Okay. That is our gradient of the objective function. Now, we also need to write gradient of the constraint, that will give us 0.5 x1 square will just give us x1 and then this will be x2. So, half and 2 will go and then x3. Okay. Now, what is the KKT condition? KKT condition, the first condition. So, we have gradient of the objective function times lambda times gradient of this is equal to 0. So, we have to write that, and then we have equality constraint. So, if what I write, this particular thing will give me that, let me change the color of the ink, so we are clear. So, I say 1 plus lambda x 1 equal to 0, okay, and all these are gradient, and we have 3 equations there, that is why we put it bar, and then 2 x 2 plus x 3 plus lambda x 2 equal to 0, and then I have x 2 plus 4 x 3 plus lambda x 3 equal to 0. So, that is what we get, right. 3 equations, and we have 3 unknowns x 1, x 2, x 3, but then lambda is also unknown, for that we have an equation also. Okay. All those equations, if you solve it together, you will get some solutions. Here all linear, so everything here, this is non-linear, this H equality constraint, whereas these are linear. So, we have to know some answer, but one thing that we can see here, if let us say x 1 is equal to 1, in which case I say lambda equal to minus 1, then the first equation is satisfied. If I also if I want to set other ones, if I say x 2 plus x 2 not plus x 2 and okay, still in the erasure ink color, yeah, x 2 and x 3 are both equal to 0, then this is satisfied, this is satisfied, and this will also be satisfied, because x 1 we made it equal to 1 here, that become 0.5 minus 0.5 equal to 0. So, this will be one solution that satisfies these 3 equations and the equality constraint. Okay. All of them are satisfied, that is, this is satisfied, this is satisfied, this is satisfied, and this is satisfied with this one. We will take that and then check it satisfies KKT conditions, mean necessary conditions, right. There is no complementarity here, because there is no inequality constraint, and lambda can be positive or negative. So, we are in fact allowing it to be negative 1 here. Okay. Now, we have to check the sufficiency condition to see if this particular point, that is x 1 is 1, x 2 is 0, x 3 is 0. Okay. If I call this x star, it satisfies necessary conditions, but is it sufficient is what we will check. Okay. Whatever I have done there is typed up here. Okay. We said that this is a solution, but it is not a solution until we check the sufficiency. So, we will check for sufficiency by writing what we call bordered Hessian. Okay. That is what we will do. For that, what do we need to do? We have to take the Hessian of the Lagrangian. We have already gradient of the Lagrangian. Okay. We need to take Hessian, meaning that this particular thing dou L delta gradient L del L, we will take another derivative and write the Hessian of the Lagrangian. Okay. Well, we can do it here, the gradient del L is here. If I say Hessian of the Lagrangian, okay. So, we need to Hessian Lagrangian is a n by n matrix, that is we have take this gradient, take another derivative with respect to x 1. If I do that here, I will get 1 not 1, it will be lambda. I am taking derivative of this thing with respect to x 1, okay. That is dou square L by dou x 1 square. This is dou L by dou x 1. So, if you that 0 is just there anyway for necessary condition, but what we need to have is the first one over there will be dou square L by dou x 1 square. Next one will be dou square L by dou x 1 dou x 2. Okay. So, we have to take this particular one, take derivative with respect to x 1 and write it over there, that is actually 0 there, and saying with this one, and then take the next one, okay, with respect to x 2 if I do, that is 0 and 0, and then I come back here and look at this respect x 2, I will have 2 plus lambda dou square L by dou x2 square, and then over here it will be x3, that will be 4 plus lambda, whereas the x2 x3 if I look at here I have 1 and here it should be 1. Okay. This will be our Hessian of the Lagrangian, okay, which is what we did the previous slide. Okay. So, which is typed up here, and noting that lambda in our case is -1, right. If I substitute I get -1, 2 plus -1 is 1, 4 plus -1 is 3. This is at this point, which point that we have taken, x1 equal to 1 and then x2, x3 are both 0. Okay. Now, if you look at this Hessian and find its eigenvalues, which you cannot do just mentally, but you can resort to a numerical analysis software like MATLAB and type this matrix and find its eigenvalues. You will find that it has a negative eigenvalue and then a positive one, another positive one. Okay. So, this is not positive definite. So, if you look at some books that do not talk about bordered Hessian, then you would conclude that this point, that is x1 equal to 1, x2 and x3 being equal to 0, you would conclude that it is not a minimum, but for this problem indeed a minimum. In fact, that is why we have taken this example to make our point that the bordered Hessian has to be checked and not Hessian of the Lagrangian being positive definite. Okay. That is an overkill, you are asking for more, while less stringent condition is good, and that is what we need to check now. Okay. Because we have constructed a problem where you do get non-positive definite Hessian of the Lagrangian, but yet the point is actually minimum because it satisfies in the constrained or feasible perturbations. Okay. So, we want to write this bordered Hessian, right. We already wrote the Hessian which is in front of us, Hessian of the Lagrangian. We also know this thing, okay, the gradient of the constraint. So, you can write this matrix. So, we have bordered Hessian when you write this H B as a matrix, we have that had 0 there, right, m by m. We have only one constraint m equal to 1, that will be just 1 0, and then we have this thing which will be 1 0 0, there will be 1 0 0, that is we have written this, and then 3 by 3 here we have to write this one -1 0 0 0 1 1 and 0 1 3. Okay. This is a 4 by 4. If you remember, bordered Hessian has a size of m plus n by m plus n. Here m is 1, n is 3. So, we have this matrix. Now, we have to look at the last n minus m principal minus, again n equal to 3 here and m equal to 1. So, n minus m equal to 3 minus 1 equal to 2. Last two principal minus, and they should have a sign of what? -1 raised to m, right. In this case m equal to 1, so it will have -1, they should be negative. The last two principal minus should be negative, right, that is what we need to have. So, we have written again in terms of lambda, but then lambda equal to in our case is -1. So, if we do all that, we get what we wrote in the previous slide, right. Sorry, this was -1, I think I made a mistake. Oh, that was it should be -1 or +1, let us see. The gradient that we had taken to begin with, that was 1, I think maybe this is the typo. Okay. So, this is not -1 then, okay, you can check it, that is not a problem. So, here if I look at it, that is, I think this is correct, this should not be minus, it should be plus, that is what we have here. Okay. And x1 was 1 for our solution. Okay. Now, if you take that last two principal minus that we had, example continued, let us see, yeah, all right. We have to take this, and last principal minus will be determinant of the matrix itself, 4 by 4 you have to take, and then so that means that you have to take determinant, okay. So, of 0, then it is not -1, 1 0 0 1 0 0 -1 0 0 0 1 1 0 1 3. This determinant if you take, that should have a sign which is negative, minus 1 raised to m equal to 1, and then we leave out the last row and last column, then we will be left with 0, 1, again that is not negative, 0 and then 1 minus 1, 0, 0, 0, 1. So, this determinant also should be negative, right. If these two are negative, then this will be a minimum satisfying sufficiency condition. Okay. So, here if my calculation is right, but for that minus 1 that is there. Okay. If last principal minus should be minus 2, this should be minus 1. So, this actually indeed a minimum and not the conclusion that you would have if you simply require that Hessian of the Lagrangian is positive definite. That is not the case here. You conclude it is not a minimum, but it indeed is a minimum. So, this is something that you should remember, this concept of bordered Hessian. To know more about it, like I said, you have to look at this book by Leuenberger. Okay. Before we leave this topic and move on to calculus of variations, one more thing that I want you to note is how do this numerical search algorithms work, right. All optimization algorithms, you start with an initial guess. So, you will have an initial guess. Okay. You start there and then you move around the space to find the minimum, local minimum that satisfies the KKT conditions. How do you do that? For that you need to have a search direction. Okay. The search direction is this thing here S, which will have a size equal to the size of x. If x is n by 1, S will also be n by 1. Then there will be this line search parameter, what we call alpha, which is just a scalar. That is, once you choose which way to go, how far do you go, right, that is set by this line search parameters. So, all the algorithms that are there that help you find the minimum with this gradient based methods differ from one another based on how they identify the search direction. By the way, this k here denotes the iteration number. Okay. You start with k equal to 0, initial guess, you will have x1, you will put that in order to find the next one x2, you have to find the search direction at 1 and then find alpha 1 and then try to find the x2 and so forth, right. Each time you take a search direction, move as far as you should and then you will go to a new point, there evaluate search direction again and move from there and so forth, one place to another place. It is like taking a bus from here to there and then take a train there and then take a bus or fly or whatever, finally you end up at the local minimum. Okay. That is how all the optimal algorithms work. Alright. Just to recapitulate this detour that we took in the last 3 lectures including this one, we have to understand KKT conditions, Cauchy-Quintana conditions are necessary conditions, and then we also looked at this feasible perturbations, consider the second order term to establish the sufficient conditions. Okay. And then particular we talked about this bordered Hessian concept, which is less stringent condition and more practical, not too conservative compared to the Hessian of the Lagrangian being positive definite. And then finally, we just talked about this algorithm, such algorithms, that is there is a search direction, okay, and then you move some distance, add it to where you are. Okay. Let us say you are the kth iteration, you find this alpha k, you have this k and then you get your k plus 1. Next iteration, keep on doing it until convergence, that is how we find. Okay. So, now we close this detour on finite variable optimization. In the next lecture, we want to calculus of variations. We will then have not just finite variables, but we will have functions as unknowns. That is what we want to have, and these 3 lectures are important because we will be harking back to these things many times to talk about our concept of local minimum, what is the gradient and what is the necessary condition and so forth. That is why we need to understand finite variable optimization and then move on to calculus of variations. Thank you.